Hello everyone, welcome to our lecture on Cartesian particle kinematics. Okay, so to start off the lecture, let me consider a particle traveling along an arbitrary path. Okay, so consider a particle along an arbitrary path or trajectory. Okay, and then we will consider the motion of the particle as viewed from a fixed Cartesian frame. Okay, and the motion of the particle is viewed from a fixed Cartesian coordinate frame. Now, one of the things that we will consider in this course is only two-dimensional motion. So this is going to be a two-dimensional trajectory. Okay, we will not be doing anything with regards to three-dimensional dynamics in this particular course. All right, so here is a fixed coordinate frame. I'm going to draw it, Cartesian coordinate frame. You're all very familiar with this from basic statics. Okay, so this is the x-axis, this is the y-axis. The unit vector along the x and the y-axis, I'm going to draw them as a little I and a little j respectively. Okay, these are the unit vectors along these directions, and I have the trajectory of the particle in the following form. So some arbitrary trajectory. Let's say that the particle is traveling from left to right. Okay, all right. The first thing that you got to understand is that wherever the particle is on this trajectory, the direction of the unit vectors will always remain fixed. Okay, so whether the particle is right here, the direction of the unit vector will always be vertical and horizontal. So this is going to be I, this is going to be j. If I'm sitting here, the motion of the particle as viewed by the unit vectors will be fixed, and so on and so forth. So wherever I am on the trajectory, the unit vectors will always be fixed in the same direction. Okay, so I'll make a note of that. Wherever we are on the trajectory, the unit vectors I and j are fixed. Okay, that's a key word here. Okay, so I and j are fixed, and the consequence of that is that the unit vectors I and j do not change with time. Okay, so this implies that for Cartesian fixed coordinates, the unit vectors I and j do not change with time. Which means that if I take the unit vector I and differentiate it with respect to time, it is going to be 0. Okay, so which means that di by dt is equal to 0, and dj by dt is also equal to 0. And this is something that we're going to be confining our analysis to at this point in time. Okay, so the unit vectors I and j do not change their directions over time, which means that di by dt and dj by dt are going to be 0. Okay, so I'm going to underline this statement as well here. Okay, so that's something important. All right, so with that particular premise, let me consider the same particle, same trajectory, and let me redraw the coordinate frame. Okay, so if I consider the particle, okay, so particle on a trajectory, Okay, so coordinate frame I and j. This is the vertical direction, horizontal direction, your usual y-axis, your usual x-axis as seen by a stationary observer. Okay, so this person who is sitting here is a stationary observer. Okay, and then I have the trajectory of the particle. Okay, the particle, let's say, is traveling along this way, starting from here and going down there. You know from before that the unit vectors don't change with the trajectory of the particle. They are always fixed wherever you are on the path. So as a consequence, this kind of a coordinate frame is also called as a path independent coordinate frame. And so I can write that statement here, you know. So these unit vectors are now path independent unit vectors. Okay, I want to maybe put a box around this particular statement itself. Okay, I think it's one of the key statements that you will come across many times in dynamics: path dependent and path independent. Okay, so we are now encountering the idea of a path independent coordinate frame. Okay, a coordinate frame whose unit vectors do not change with the path of the particle. Okay, so I'm going to write that statement here. So we are now on a path independent coordinate frame is a coordinate frame whose unit vectors do not depend or change along the path of the particle. Okay, so this is also a key statement here. And for us, the Cartesian coordinate frame is going to be a path independent coordinate frame. Okay, so we are going to consider a path independent Cartesian coordinate frame. Okay, so we are on a path independent Cartesian frame. Okay, all right. Then what I can do is the following. If I have, I come back to the trajectory and I have this important line underneath it. I'm just going to take this stationary observer guy and then maybe scoot that down here. Okay, maybe I can bring that down here. Okay, all right. So I'm going to draw a position vector from the point O, the fixed point O. Let me consider some point in the trajectory. Okay, so let's say that this is some point P of t. Okay, at some point in time. Then I'm going to draw a position vector which is fairly straightforward, right? Starting from the observer's position, this is the position vector r of t. Okay, so r of t is the position vector. All right, then acceleration vector at the same point is tangential to the path of the particle, so the acceleration vector is going to be drawn in that particular manner, tangent to the path at that point. Okay, it's approximately tangent as far as I know, and this is v of t, and v of t is the velocity vector. And lastly, I'm going to have the acceleration vector whose direction I'm going to draw, but we will figure this direction out in some time, okay, when we start discussing the normal tangential coordinate frame. Okay, so perhaps it is sitting somewhere here. Okay, and let me point that out this way. Okay, so that's the particle's position, and then this is a of t, and a of t is the acceleration vector. All right. Now I'm going to start writing these in terms of their components along the x and the y directions. Okay, so let's start with the position vector. Okay, so let us say that r of t, let us say it has components. I'm sorry, my t doesn't look like a t. So say components along x and y are given as rx and then ry. Okay, they could both be changing with time, so maybe I should write them as functions of time. Okay, rx of t, ry of t. Okay, then the velocity vector, okay, once again is also going to have components along the x and the y directions as vx and then vy. Okay, and then the acceleration likewise will have components along the x and the y given as ax of t, ay of t. Okay, so if that is the case, then here is what I can do. Okay, so this tells me that from the Cartesian frame, Cartesian representation, the position vector, as you know, if you have a component along the x-axis, component along the y-axis, any vector is its magnitude times its unit vector. Okay, so something that you want to maybe make a note of. Okay, so any vector is its magnitude times unit vector. This is a general statement. Valid for any coordinate frame. Okay, and if I make use of that, then I can say the following. Okay, position vector r of t is going to be some rx of t in the I direction, ry of t in the j direction. Okay, this is the Cartesian representation of the position vector. Then I go to the velocity vector. Velocity vector is the rate of change of the position vector. Okay, which means that this is going to be d by dt of rx of ti, ry of tj. Just bear with me while I do this. I'm making use of the product rule. Okay, so this is going to be drx by dt I and rx of t times di by dt plus dry by dt j ry of t times dj by dt. Okay, making use of the product rule of differentiation. But then you basically see that di by dt, dj by dt are 0, so knock those guys off their perch. This is gone, that's also gone, which means that I end up with the following. Okay, so this means that v of t is going to be drx by dti dry by dtj, which can be written as vxi vyj, which tells me that vx is drx by dt and then vy is dry by dt. Okay, so this is the corresponding components of acceleration in the x and the y directions. And I can do the same thing for the acceleration vector. I'm going to skip some of the details. Acceleration vector is going to be dv by dt, which is d by dt of Vx and then Vy, and so this is going to be dVx by dt dVy by dt, because the unit vectors I and j do not change with time. So this implies that acceleration can be written this way, or it can be written in terms of its components axi, ayj. Okay, and this tells me that, okay, hey, from this it is very straightforward to see that ax is equal to dvx by dt, but dvx by dt is already drx by dt, so this is also the second derivative, d square rx by dt square. Okay, and then likewise ay is going to be dvy by dt, and this can be written as the second derivative of the position vector. Okay, so these are terms of importance, and these are the components along the x and the y directions. All right, thank you for your patience, and then I'll see you in the next concept talk. Bye bye.